Good morning, and thank you all for joining. I'll be presenting results from a project that I've been working on for the past year with my collaborators. That's Andrea Fossbender, Yvonne Wong, Mariana Biff, and Mega Stapa. Our initial motivation for this project was to derive net primary production using profiling float observations, which is similar to previous work done by Mega Stapa in the North Atlantic, but focusing on the differences between getting those depth resolved estimates and those derived from satellites, which are of course just seeing the upper layer of the water column. And then during this study, as you're all well aware, there was a new marine heat wave that happened in our region of focus. So that kind of shifted our study focus into looking at the context of this recent marine heat wave and the previous marine heat wave in relation to net primary production. And also I'll be talking a bit about net community production. So first, let's do a quick review of what net primary production is and also versus what net community production is. So in this production chain, we start with phytoplankton photosynthesizing, that's all these little green bugs, and they're making organic carbon, which goes into this gross primary production bank. And then some of this carbon is used by these phytoplankton to run basal metabolic needs. So we can call that autotrophic respiration. And then some of that goes to the bacteria into heterotrophic respiration. So if you take into account that basal metabolic need by phytoplankton, the autotrophic respiration, you get net primary production. And then if you go one step further and take into account that heterotrophic respiration, you get net community production, which is basically the baseline of carbon that may be exported from the upper sunlit ocean. And if you're quick, you might have already put together that the difference between these two, net community production and net primary production, is heterotrophic respiration. So that's kind of the takeaway from this that I'd like you to remember when we look at the results. If we're seeing NCP, net community production, and NPP, net primary production, not follow each other, if there's divergences in that, it may be explained by increases or decreases in heterotrophic respiration. So now let's get into the calculation of net primary production. There are, of course, methods to do this directly, but as we're all aware, it's very difficult to get direct observations. So what we're interested in doing is finding a method adaptable to autonomous observing platforms, because that can give us a global coverage, it can give us a much better temporal scale. And so we've kind of honed in on this one model, there's many, the carbon-based productivity model, which was initially laid out in 2005 by Barenfeld et al., and then adapted in 2008 by Westbury et al. And later, it was brought on by Mega Stapa in 2019 and adapted to floats, as I mentioned previously. That's the citation here if you want to look into it. And the foundation of this relationship to get at NPP is based on the equation shown here, which is the product of growth rate and carbon. So to get growth rate, which the Greek symbol for that is this letter mu, you can use this equation, which is included in the Westbury 2008 paper, where you need an estimate of chlorophyll, you need an estimate of carbon, and you also need an estimate of photosynthetically available radiation, or PAR, P-A-R. And then for carbon, you can get that from a backscatter estimate. And here we're using the coefficients described by Graf et al. In 2015 to convert backscatter to carbon. And doing these calculations for mu, for growth rate, for example, and carbon have been done and adapted to floats in many previous studies. So this part definitely isn't anything new. The biogeochemical profiling float observations I'll be talking about are from this region near Ocean Station Papa, the Northeastern Pacific. Most of these floats were deployed through a collaboration between MBARI, Monterey Bay Aquarium Research Institute, where I am, and the University of Washington. The first float was deployed in 2008, shown here. It carried the standard CTD Argo instrument and with an addition of an oxygen and nitrate sensor. So since then, since 2008, we've had a continuous time series of these variables in this region from all these floats shown here. These are also the float paths shown in the map. And then since 2010 to present, we've had a near continuous time series of those above variables with the addition of chlorophyll, backscatter, and CDOM. And two of those floats actually were deployed just recently in 2018 through a collaboration with NSF and the NASA exports team. And those also included a pH sensor, which is really exciting. And then you might have noticed that two of these variables here are two that we need to finally estimate net primary production. The other two being PAR, which unfortunately these floats are not equipped with, but they will be in the future, which is really exciting. And then mixed layer depth, which we're estimating using the approach by Holt and Talley for using a density threshold. And then for reference, the triangle shows the location of Ocean Station Papa, which is where a NOAA mooring has been operating continuously since 2007, and the dots indicate the station locations for the Canadian Line P cruises, which are conducted 3 times per year, giving us an amazing long-term record of discrete observations, such as high-performance liquid chromatography samples, which we used in order to adjust our fluorescence measurements from the floats to chlorophyll A measurements. And then also all of this data, which includes 8-day average satellite MODIS data, specifically biogeochemical float data, and the Line P data has been restricted to this black box region so that we can kind of focus in on this Ocean Station Papa OSP area. And again, these are the variables that we need to calculate NPP using the CBPM algorithm, which will each be used for each device. So all chlorophyll backscatter and the mixed layer depth will be constrained to satellite observations versus float observations, whereas PAR will be having to use float observations for both types of estimates of NPP, satellite and float based. And here's the real results. So the float-based estimates of integrated net primary production are shown in green. The satellite-based are shown in gray. The standard deviation is the standard deviation over that box region. And the bottom figure shows the areas where this data was collected at the same time. So we're looking at the integrated NPP from satellite versus integrated NPP from float observations. And we see that they agree relatively well. Generally, they trend positively. So if you have high annual NPP in the satellite OBS, you have high annual NPP in the float OBS. And besides some spatial temporal differences that are inherent to using these two different types of platforms, there may be some more systematic factors that we can get into. And there's majorly two that I want to talk about. So the first, which might be the most obvious, is that we're using different sensors on each platform. And they measure these input variables in different ways. So for example, the satellite is measuring absorption of chlorophyll. The float is measuring chlorophyll based from fluorescence. And so if you look on the graphs to the right, you see the difference between the float input data on the x-axis and the satellite input data on the y-axis. And there's some scatter in all of these comparisons, but the most scatter is in chlorophyll, which may end up leading to differences between these estimates later on. And then the second major factor that may lead to kind of more systematic discrepancies that we can look into is that we're comparing depth resolved data to data that's collected just within the first optical depth. That would be what the satellite sees. So the first optical depth, the representation of that shown here is in pink. The mixed layer depth estimate is in orange. And you can see that the satellite for the CBPM algorithm, it can only see the upper water column area, the first optical depth. So it takes the average of that and then kind of assumes everything is homogeneous throughout the mixed layer. So as you go through depth, you see CBPM is relatively consistent through the mixed layer. And then after that, it attenuates with light attenuation. Whereas the float is actually able to see all of these changes in chlorophyll and carbon throughout the water column. And in comparing climatologies of float and satellite integrated net primary production, there's some clear seasonal differences. So on the right, we're looking at satellite results for each year are shown in the colored lines in the background. And then monthly climatology is shown as the black line. And on the left, we have the same, but for the float integrated net primary production results. And behind each are direct observations of NPP, but unfortunately, take these with a grain of salt. They were collected some 40 to 20 years ago, making direct comparisons between these pretty difficult. But we can at least illuminate these factors that might be forcing these discrepancies, that there's like a clear seasonal discrepancies by separating them out. So again, these are monthly climatology plots. Let's focus on the one on the left. We've taken that same satellite data that I showed previously, the integrated net primary production data. All the years are shown in colored lines, and then the black line indicates the climatology. And then instead of taking the difference of that minus the float derived estimate of NPP throughout the entire water column, we've taken just the float average data within the first optical depth and acted as though that was a proxy for what the satellite's seeing, and then used the same satellite method for CBPM to get an estimate of integrated net primary production. So essentially what we're looking at here is we're getting at the differences between the input variables, so that first issue. And we see that there does seem to be a systematic seasonal discrepancy between the two. And then the middle panel shows the difference between that same optical depth averaged float data, so kind of a proxy for satellite, and then minus the actual depth integrated data of float NPP. So now we've removed any weirdness between satellite input variables versus float input variables, and we're just looking at how the algorithm does in making assumptions with depth versus the actual depth measurements. And the plot all the way to the right is actually just basically the difference between these two, or if you take the sum of the left and middle graph together. And that's what we're actually observing as differences. So we can see that there's kind of these two counteracting effects seasonally that's ending up with a more similar NPP result than you might expect. And then also keep in mind that now we're just looking at integrated net primary production, but there's a lot of stuff going on with depth that we can look at too. So let's take like this middle figure and expand the time series back out, and we're gonna look at the difference with depth as well. And that's what we're looking at here. So again, this is only showing float data. It's the difference between NPP derived from just the optical depth average float data and then derived through depth as CBPM does for satellites, minus the depth resolved float estimates of NPP. And not too surprisingly, we see the major differences occur when we have an increase of the mixed layer below the photic depth, because the original CBPM assumes that everything's kind of homogeneous throughout the mixed layer, whereas you probably don't have as much primary production underneath the photic depth. This is kind of a well-known issue with the CBPM model, but now we're just graphically representing it. And we also see that, so in addition to the seasonal or the differences between this that are kind of counterbalancing each other, we also see a systematic bias with depth, where you're overcompensating and undercompensating at the same time. So again, you're kind of reaching a similar value, but it might be by accident. Okay, so for now, I'm gonna set that aside. The main takeaway is the satellite observations and float observations do kind of trend each other, but there's definitely some more things that we wanna look into, especially since the systematic biases seem to be definable. And then we may be able to go back and kind of adjust satellite data based on these results. So now let's go and focus on why we're all here to talk about the marine heat waves. So a little bit of background, we're all obviously familiar by now. There was a marine heat wave termed the blob back in 2013 to 2016. And then we recently had a return of the blob in 2018 through 2019. And especially for the first event, there have been many studies on the effects of this anomalously warm water on the region's ecosystem. But in the interest of time, I'm just going to mention these two studies because they're very pertinent to this talk and to looking at our results later. So Biff et al. In 2019 and Yang et al. In 2018 each used the same profiling floats as this study region to get estimates of annual net community production. Though they found that there was a major decline associated with these warming events, they found that this decline happened in different years, and that may be a result of them using pretty different approaches at calculating net community production. So Biff et al. Used a nitrate-based estimate, and they constrained their observations to above the photic depth, whereas Yang et al. Used an oxygen-based measurement, and they used the maximum winter mixed layer depth to get NCP. And because heterotrophic respiration may be included when integrating below the photic depth to maximum winter mixed layer depth, we'll be kind of more comparing our results to that of BIFs to only focus on comparisons of net primary production to the maximum annual net community production. Okay, so looking back at that same time series as before of NPP, now I've just added an indicator of SST anomaly, which it's not super robust. It's actually just based on taking the monthly climatologies of this time series that you see here from MODIS satellite SST data. And then for each 8-day average satellite value, we've taken the difference of that from its monthly climatological mean. So immediately you can see in 2013 through 2016, that first blob event really stands out. And then in 2018 onward, we see that second blob event ramping up. And the most interesting thing that kind of sticks out now that we can see is the year following the first year of anomalously, or the first winter of anomalously warm waters, we see a major increase in NPP. So for example, in 2014, and then in 2019, we see a major increase. And then in the bottom figure, we've taken annual net primary production anomaly values from this long-term satellite record on the y-axis versus mean annual sea surface temperature anomalies on the x-axis. And we've colored them by year. And you can see that those 2 years, 2014 and 2019, really stand out. And although this data set's pretty small, we do find a statistically significant relationship between annual NPP and SST anomalies. And of course, we can also look at this through depth, which is now shown in the middle panel. So this is showing NPP in the green colors. And again, the first optical depth is in pink, the mixed layer depth is in brown, and then the photic depth is shown in gray. And we see coinciding increases in oxygen with increases in net primary production, which is pretty expected, especially more focusing above the mixed layer. And then here is carbon, again, which was calculated from backscatter from our float sensors with depth. And here we see, again, changes with NPP coincide with increases in carbon accumulation, especially during these 2 years of major ocean warming.
Jackie, just letting you know, you got about 1 to 1.5 minutes left.
Oh, cool. We're wrapping up. All right, so here we're getting back to net community production. So I've just added annual net primary production anomaly on the top and highlighted those 2 years of major NPP increases in magenta. So you can kind of focus on those. And we see that in the first year of this marine heat wave, there's a high increase in NCP and NPP. And then that second year where NCP kind of crashed in Biff's study, which is this data was taken from our 2019 paper, we see that NPP remains anomalously high. So this kind of gets at that NPP or NCP is driven more by the heterotrophic respiration rather than NPP directly. Oops. And this is, in fact, what collaborators Yibin Wong and Andrea Fossbender are now working on. They're evaluating the photic zone NCP using nitrate oxygen and dissolved inorganic carbon tracer budgets. And Yibin is finding results similar to those of Biff et al. 2019, as well as reduced particulate inorganic carbon or calcium carbonate production during these warmer events. And in interest of time, I'll just leave the summary slide up. Somehow.
Wonderful. Thank you so much, Jackie. That was a really cool look at the heat waves from a different perspective than these earlier talks.
Thanks. And then here's,
yeah.
Thank you.